Have you ever felt your brain just hit a wall, like you're trying to learn something new or tackle a really complex problem, but your mental gears just seem to seize up?
Yeah, that feeling.
That overwhelming feeling, right? That sense of mental exhaustion. It actually has a name: cognitive load.
Mm,
So today, we're going to embark on a deep dive into cognitive load theory. CLT, they often call it. It's a really powerful concept that not only explains why our brains sometimes feel like they're about to, burst,
right.
but also what we can actually do about it.
And this isn't just some abstract psychology thing either. We're actually going to explore how understanding cognitive load is, well, kind of a crucial shortcut to being genuinely well-informed.
Okay.
Whether you're trying to master a new skill, maybe write more effective code, or even build more resilient, more efficient data systems, you might be surprised by some of the insights we dig up.
Sounds good. We've pulled together a fantastic stack of sources for this deep dive. Everything from the foundational psychological research that really started it all,
Right, the classics.
to practical guides on modern software development, and even diving into the intricate world of data engineering. So let's explore this invisible weight that shapes our mental performance.
Let's do it.
Okay, so at its core, cognitive load theory, CLT, it's basically a psychological framework. It explains how our brain processes information and, really critically, how that impacts our ability to learn.
Mhm.
The fundamental idea is, well, it sounds simple. Our cognitive resources, especially our working memory, they're incredibly limited.
That's such a crucial point. Think of your working memory as like a mental notepad,
Hmm.
a temporary holding space, but it's got a really small capacity.
Right.
It can only juggle, a few pieces of information at a time and only for a short while.
Right.
When that capacity gets exceeded, well, it's like trying to pour more water into a glass that's already full.
Or finding all the parking spaces are taken, yeah.
Exactly. Your brain simply can't fit any more in at that moment.
And this idea, the limited capacity thing, it's not totally new, is it? I remember reading something. It connects back to some really pioneering work from George Miller back in 56.
Oh, yeah. Miller's work. Absolutely.
His famous paper, The Magical Number 7 plus or minus 2, that research explored human memory limits, suggesting we can typically hold, about 7 bits of info, give or take?
7 chunks of information, yeah. In short-term memory at any one moment. That was quite a revelation back then.
It really was.
And building on that understanding, that memory limit idea, it was John Sweller, an Australian educational psychologist, who formalized cognitive load theory back in 1988.
Okay, Sweller.
Yeah. He specifically connected it to the mental processing needed for problem solving and maybe more importantly for creating what he called schemas.
Schemas, like mental models.
Exactly. Our mental models are frameworks for how information is organized, how things work.
Yeah.
He was really looking at how we build expertise, how we internalize knowledge.
So, Sweller outlined 3 distinct types of cognitive load that affect how we learn. First, there's intrinsic load.
Right.
This is the inherent complexity of the stuff you're trying to learn. Like, trying to learn advanced calculus is just harder intrinsically than learning basic arithmetic.
Yeah, sure. Makes sense.
It's got a higher intrinsic load. And this type, it's generally hard to change because it's kind of baked into the topic itself, right? Though I guess it depends on what you already know, too.
That's a factor, yeah.
Yeah.
Your existing schemas matter.
Then there's extraneous load. This one comes from, distractions or irrelevant stuff in the learning environment, and it's often down to poor instructional design.
Oh, yeah, definitely.
Like, imagine trying to read an important report, but it's crammed with distracting pictures, loads of jargon you don't need, maybe even gasp, blinking text, or something awful.
Ugh, yeah, the worst.
That extra mental effort you spend trying to filter out all that noise, that's extraneous load.
Yeah.
It just burdens your working memory without helping you learn anything.
Burns up those limited
Yeah.
slots.
Exactly. And finally, number 3 is germane load. This is the mental effort we put into actually connecting new information with what we already know, building those new schemas.
Okay, so this is the useful kind.
Yeah, this is the good cognitive load, the productive kind, because it directly helps build long-term memory. Like, if you successfully apply a new coding concept to a problem, you already understand that effort, that connection making. That's germane load.
That's the critical distinction, yeah.
Mm,
The core insight from CLT is that if you want to design really effective learning experiences, whether it's for yourself or someone else, you need careful management.
All right.
You want to, well, intelligently manage the intrinsic load, actively minimize the extraneous load, get rid of the junk, and strategically maximize the germane load. That's the sweet spot.
Because what happens when your overall cognitive load, the sum of all three, just gets too high? The effects are pretty bad, right? And you probably felt them.
Oh, absolutely.
You get reduced comprehension, things just don't sink in. There's increased frustration,
Yeah.
stress, makes you want to just give up.
Can even lead to increased stereotyping, interestingly, because your overwhelmed brain just falls back on subconscious shortcuts.
Right. And crucially, decreased retention. The information is way less likely to actually make it into your long-term memory.
Yeah, it just washes over you.
And of course, your performance tanks. It has really real, often painful consequences when you're overloaded.
For sure.
So if this invisible weight, this cognitive load, has such big real-world impacts, how do we actively manage it? Especially when we're trying to learn something new and maybe difficult. Let's get practical.
Absolutely. Okay, so while intrinsic load is inherent, like we said, you can mitigate its impact. Strategies for, let's say, intelligently managing intrinsic load.
Okay.
First, chunking. Breaking complex stuff into smaller, more digestible pieces. That's why microlearning is so popular, right? Little
Oh,
bites.
makes sense.
Second, using visual aids. Diagrams, charts, images. They help represent complex ideas visually. Our brains are wired for visuals. It often reduces the need for tons of text.
Yeah, I find diagrams super helpful.
Third, simplification. Using analogies, metaphors to explain key concepts, like, explaining a computer network as a postal service or something. It gives you a hook.
Right, a mental model to start with.
Fourth, providing context. Explaining why the material matters to the learner, to their life, their goals. That boosts motivation, makes the intrinsic load feel less burdensome.
Okay.
And finally, offering hands-on opportunities, letting people practice, apply what they've learned through actually doing it. Experiential learning really helps make abstract things concrete.
So those help with the inherent difficulty. What about reducing extraneous load? The distractions and clutter.
Right. This is about creating that winning learning environment. So one key is clear instructions.
Yeah.
You need clearly stated goals, expectations, how you'll be assessed, no guesswork.
Yeah, ambiguity is killer.
Totally. Another is obviously minimizing distractions. Turn off notifications, find quiet, maybe use noise-canceling headphones. Basic, but crucial. It's also important to avoid redundancy. Summarizing key points. Good. Unnecessary repetition or showing the same info in slightly different confusing ways. Bad. Just adds clutter.
Okay.
Also, offering support, like a social learning environment, maybe mentoring programs, that can reduce the feeling of being isolated with the burden.
Community helps.
Definitely. And don't underestimate just being positive. Fostering a supportive vibe, encouraging a growth mindset. A calm mind is generally a more receptive mind.
Good points. So intrinsic managed, extraneous minimized. How do we maximize germane load, that good stuff, the connection making?
Okay, several really effective strategies here. One is activating prior knowledge, like brainstorming or asking relevant questions before you start the new learning. It warms up the right brain pathways.
Primes the pump, sort of.
Exactly. Another is encouraging reflection, allowing enough time and space to connect different topics, to think, okay, what does this actually mean? How does it fit?
Right, not just rushing through.
Elaboration is also key. Asking learners to explain new stuff in their own words, come up with their own examples, connect it back to things they learned before. That active processing really strengthens the connections.
Once you own it.
Yeah. Scenario-based learning is great too. It helps learners see the relevance immediately, apply concepts to sort of real-world situations, makes the connections explicit.
Okay.
And finally, feedback. Timely, specific suggestions. It helps learners fix misconceptions and really solidify their understanding. Guides that schema building.
And technology, I guess, plays a big role in all this today. LMS systems, apps.
So huge.
Yeah.
Yeah, learning management systems, various apps, they're often designed specifically to break down info into those chunks we talked about.
Right.
And interactive elements, simulations, games, quizzes, they're not just for fun. They actually encourage that active processing, which is exactly what you need for building germane load.
Makes sense. Okay, let's zoom in now on a field where, well, mental gears are constantly grinding. Computer programming.
Oh yeah, prime territory.
Inherently complex, highly mental work. How does cognitive load specifically affect programmers day to day?
Well, what's really fascinating here is a specific study that dug into this. They used eye tracking data from 216 programmers. It was from the EMIP dataset Eye Movements in Programming.
Eye tracking. Wow.
Yeah, they carefully look at factors influencing cognitive load while programmers were just trying to understand code. And they linked subtle eye movements, things like changes in pupil diameter, saccadic movements.
Jacadic, like the quick jumps your eyes make.
Exactly. Those quick simultaneous jumps your eyes make when you read or scan something. They link those patterns directly to a programmer's cognitive load.
That's amazing. So, based on that, what factors did they find had the biggest impact on a programmer's cognitive load? This sounds really interesting.
It really is insightful.
Yeah.
Okay, the research found that age actually had the highest effect. It accounted for over 18% of the impact, and the load tended to increase with age. Then there's linguistic distance. This was a really novel finding. The distance between a programmer's native language and English had a significant effect over 15%.
Linguistic distance. You mean like how similar their first language is to English?
Exactly. For example, they found Chinese was most distant from English in this context, while maybe Italian was closest.
Wow. And that matters because,
Well, think about it. Programming languages overwhelmingly use English-based commands, keywords, syntax.
right, if, else, while.
Precisely.
Yeah.
So the study suggests that your foundational native language literally shapes how easily your brain can process these abstract logical structures and the new syntax. It's not just memorizing commands, it's about how deeply those patterns resonate
Yeah.
or clash with your innate linguistic framework.
That's a really interesting angle. What else?
And finally, maybe less surprising, programming experience in the specific language being used also had a significant effect. The more familiar you are, the lower the load, generally.
Okay, that makes intuitive sense. What about gender? Did that play a role?
That's another notable finding. The study found that gender difference has a limited effect on cognitive load in computer programming processes. It barely registered, like 0.255%.
So, pretty negligible.
Yeah, and that lines up with broader research suggesting, biological gender differences don't really strongly explain cognitive abilities in fields like programming.
Okay. So, what does this all mean for you if you're, say, learning to code right now or thinking about it?
Well, the study kind of hypothesizes that maybe teaching programming languages like spoken language can be meaningful and beneficial, suggesting things like continuous exposure, focusing on intuitive patterns. It might actually make a real difference in lowering that initial cognitive barrier.
Interesting. Treating it less like abstract math and more like language acquisition.
Kind of, yeah. It's a thought-provoking idea.
Okay, let's pivot a bit. From learning about programming to the actual doing of programming, and maybe software design more broadly, our sources really hammer home this critical point. Confusion costs time and money in code. And that confusion, that cost, it's often caused by just too much extraneous cognitive load baked into the software itself.
This is a huge point, because remember that working memory limit, roughly 4 chunks of info.
Right. Miller number, sort of.
Yeah, well, that applies when we're just reading code, too. And given that we spend way, way more time reading and understanding existing code than writing new code,
That's true.
designing to reduce cognitive load isn't just about writing clever or compact code. It's about writing code that's fundamentally understandable, easy to get your head around.
Okay, so give us some concrete examples. Where does this extraneous load creep into software and how do we fix it?
Sure, take complex conditionals. Those monster if statements packed with NMN and operators. If L, constant man and statical, condition 3, condition 4, and
Yeah.
serial dot condition 5.
Yeah, makes my head spin just hearing it.
Exactly. That's a ton to hold in your working memory. The simple fix: introduce clear, self-descriptive intermediate variables, like is valid, value L constant, is allowed condition 3, is secure condition 4 and a dot condition 5. Then your if just reads if is valid and allowed and is secure. Much easier.
Okay. Breaks it down. What else?
Nested if statements. Going deep, like if. That forces your brain to constantly track all the preconditions.
Yeah, you get lost in the layers.
A much better approach is often using early returns or guard clauses. Check the error conditions first, exit early if they fail, and then the main logic just focuses on the happy path.
Yeah.
Frees up so much mental space.
Good one. I see that a lot.
Then you have the classic inheritance nightmares, where you see these long chains,
Yeah.
like admin controller extends, user controller extends, guest controller extends, base controller.
Oh, boy.
To understand anything in admin controller, you basically have to mentally reconstruct that entire chain, figure out where methods might be coming from. It creates an enormous amount of cognitive load.
So what's the fix there?
The widely accepted solution is prefer composition over inheritance. Break functionality into smaller, independent components, like little building blocks that can be combined or composed as needed. It's far less mentally taxing to understand.
Right. Less hidden magic.
Exactly. Another common trap is this well-meaning idea that methods should be super short. like under 15 lines, or classes should be tiny.
Yeah, I've heard that advice.
It can be misleading. Our sources talk about shallow modules. These are things with complex interfaces, lots of methods, maybe complex setup, but they only do something small or simple inside.
Okay, so what's the problem?
The problem is you end up with tons of these tiny, shallow modules, and you have to track all the interactions between them across many different files. It's incredibly taxing mentally.
Ah, I see. The complexity is just shifted to the connections.
Precisely. Instead, the goal should be deep modules, powerful functionality hidden behind a simple interface. Think of the classic Unix I/O example. There are literally hundreds of thousands of lines of code doing complex stuff under the hood. But it's all hidden behind just 5 simple system calls. Open, close, read, write, seek. That's deep, powerful, and ultimately simple to use because the cognitive load on the user is low.
That's a great example. Deep module, simple interface.
And related to that, the true single responsibility principle, SRP. It's not just about a module doing one thing. It's that a module should be responsible to one and only one user or stakeholder.
Okay, that's a subtle difference.
It is, because if you make things too granular, like with microservices sometimes,
Yeah.
you can end up with what's called a distributed monolith.
Distributed monolith sounds like an oxymoron.
It kind of is. Technically, they're separate services, but they become so tightly coupled, so chatty, so complex in their interactions that they basically behave like one giant unwieldy system again. And diagnosing problems. Forget about it. The cognitive load just skyrockets because you're tracing requests across dozens of tiny interconnected parts.
Right, so it makes you ask, are you paying this huge cognitive load price for abstractions that aren't actually delivering the promised benefits?
Exactly that question. Are the abstractions helping more than they're hurting your ability to understand the system?
It's also interesting, our sources mention how even really feature-rich programming languages can, maybe ironically, increase cognitive load.
Yeah, because then developers have to spend mental energy figuring out why a programmer decided this was the way to approach a problem from all the features that are available in that language.
Right, too many choices.
The insight there is pretty clear.
Yeah.
Sometimes you can actually reduce cognitive load by limiting the number of choices, maybe using a subset of the language or establishing clear conventions. Less is often more for understandability.
That makes sense.
And this ties into another useful mantra. A little copying is better than a little dependency.
Okay, explain that one. Sounds counterintuitive, maybe. Don't we want DRY code? Don't repeat yourself?
Generally, yes. But think about pulling in a huge complex library just to use one tiny helper function from it. Now, all your dependencies are your code, in a way. You're responsible for them. And you'll spend potentially painful amounts of time debugging issues within that massive external library when things go wrong or when it gets updated and breaks something. That adds significant extraneous load. Sometimes, just copying that small function directly into your code base is simpler, lower cognitive load in the long run.
Ah, okay.
But
avoids the hidden complexity of the dependency. Got it.
we also see extraneous load when, say, business logic gets hidden inside things like HTTP status codes.
How so?
Like maybe your API uses a 401 unauthorized status to mean your JW key token has expired, but a 403 forbidden to mean you don't have permission for this specific action.
Right, I've seen APIs like that.
It creates unnecessary cognitive load for anyone using your API. They have to memorize your specific non-standard mapping. It's much clearer, much lower load to just return self-descriptive strings directly in the response body, like code, cheat_around expired, or code permission denied. It's immediately obvious what happened.
Yeah, explicit is better than implicit magic.
Absolutely. And surprisingly, even some popular, well-intentioned architectural patterns, things like layered architectures, maybe hexagonal or onion architectures,
Yeah, those are common.
they can sometimes add indirection and extra glue code that actually makes troubleshooting more difficult than they simplify. They often promise quick replacement of components, like swapping out a database.
Right, that's the sales pitch.
But the real pain in distributed systems usually isn't just swapping one component. It's dealing with data modeling compatibilities, communication protocols, distributed systems challenges, and implicit interfaces between components. So again, you have to ask that hard question. Are you truly gaining enough flexibility to justify the higher cognitive load these extra layers of abstraction introduce?
It really comes down to trade-offs, doesn't it?
Always.
So, the big takeaway here for software seems to be that familiarity is not the same as simplicity.
That's a fantastic summary of it. Old code, code you've worked on for ages, often accrues cognitive load gradually. Little complexities get added here and there.
And you stop noticing them because you're used to it.
Exactly. You develop workarounds, mental shortcuts.
Mm.
You don't see the burden anymore. That's why it's so valuable to get fresh eyes on it. Involve junior developers, or like our sources said, the new kid.
Yeah. Why them specifically?
Because their fresh, unbiased perspective is invaluable. They haven't internalized all the weird workarounds yet. They'll immediately spot the mentally demanding areas, the confusing parts, the things that make them go, huh. That feedback is gold for reducing cognitive load before it becomes totally intractable.
Get the newcomer's perspective. Great tip. Okay, let's switch gears slightly and apply this cognitive load lens to another critical area, data pipelines.
Ah, yes. The backbone of modern business intelligence.
Often described as factory assembly lines for an enterprise's digital ecosystem. Super crucial. Yet our sources tell us something pretty stark. 77% of organizations struggle with data quality.
Wow, 77%. That's huge.
Yeah, and it significantly impacts performance, reliability, basically everything downstream.
And this is precisely where human cognitive load crashes head-on into system complexity.
Right.
You've got messy data, maybe inefficient transformations, system bottlenecks. All this stuff can just cripple even the best engineered ETL pipelines.
ETL extract, transform load, the processes that move and shape raw data into something useful.
Exactly. And this whole domain is just overflowing with opportunities for cognitive overload for the engineers managing it.
So let's talk about some common ETL challenges that are really tied to this cognitive burden. What are the big ones?
Okay, first up, a classic. Scalability and performance bottlenecks.
Right, things grind to a halt.
Yeah, as data volume grows, jobs just slow down dramatically. This could be due to poor data partitioning, meaning your system scans way more data than it needs to,
Okay.
or excessive shuffle operations. That's where data gets heavily redistributed across all the machines in your cluster. It's a huge bottleneck in distributed systems like Spark.
The network becomes the problem.
Big time. Or even just using inefficient storage formats like plain old CSV or JSON files, instead of optimized columnar formats like Parquet or ORC.
Why are those better?
Columnar formats let you read only the specific columns you need for a query instead of scanning entire rows.
Yeah.
Massive performance difference for analytics. And even simple things like cluster spin-up times add what engineers call dead time, just waiting around, losing context, adding to the cognitive friction.
Okay, so how do you tackle those performance issues from a cognitive load perspective?
Well, the solutions aim to reduce that waiting, that friction. You optimize your partitioning strategy. You work to reduce those costly shuffle operations, maybe using techniques like broadcast joins to keep data local.
Avoiding the shuffle.
Right. Switching to Parquet or ORC makes data access way faster. And for things like high memory use or those annoying cold start delays, you can tune your Spark memory settings. Or maybe use cloud services like AWS glue streaming jobs or interactive sessions, which keep compute clusters warm and ready to go. Less waiting, less context switching. Got it. What's another major challenge area?
Workflow orchestration and tooling complexity. This is huge.
Yeah.
Managing all the dependencies between different data jobs, scheduling them correctly, handling errors when one part fails. It gets complicated fast.
Yeah. Pipelines are rarely just one step.
Exactly. And you've got various tools, maybe AWS Glue workflows, maybe open source tools like Apache Airflow or AWS Step Functions, Dagster. They all have different trade-off, the different mental models you have to learn. And a failure in just one step can cause cascading issues through the whole pipeline.
Leading to frantic debugging, more cognitive load.
Totally. And a core problem is often that some tools lack good built-in dependency tracking, or they have really basic default retry behaviors, meaning failures might just disappear, or they get retried immediately and inefficiently, maybe overloading a downstream system. It adds to the mental load of just figuring out what actually happened.
So what are the solutions there? Better tooling helps. Using advanced sensors or triggers for dependencies, setting up more fine-grained, smarter retry policies, and critically, establishing really good centralized logging and alerting so you catch issues quickly and clearly, reducing the mental effort needed to spot and diagnose problems.
Makes sense. Visibility is key.
Always. Then there's data consistency and reliability. Big headaches here.
Like what?
Things like late arriving data messing up your reports because it missed the processing window, or duplicate records sneaking in, maybe from job reruns, or because streaming systems often have at least once delivery semantics.
Right, guaranteeing it arrives, but maybe more than once.
Exactly, which you then have to deal with. Mitigation strategies include using watermarking for tracking event time in streams, using merge or upsert operations to handle updates correctly, maybe event-driven reprocessing for late data, or using specialized tools like Delta Lake or Apache Hudi, which are designed to handle historical data updates and deduplication more easily. Again, offloading the complexity.
Okay, and another big one you mentioned was schema evolution and data quality.
Oh yeah, this is a constant battle. Unexpected changes to data structures upstream, unplanned schema changes, can silently break transformations downstream.
Silently being the scary word there.
Absolutely. You might get data loss, misaligned columns, corrupted results, and you might not notice for a while. Even automated tools like AWS glue crawlers, which try to infer schemas automatically. They can sometimes misclassify data types or really struggle with deeply nested JSON. They're not foolproof, requires human oversight.
So, what are the best practices to manage that cognitive burden?
Again, it's about reducing surprises. Use schema evolution-friendly formats like Avro, which are designed to handle some changes gracefully. Often, it's better to manually define schemas for critical pipelines rather than relying solely on auto-inference. Control is good.
Takes effort up front, but saves pain later.
Exactly. Employ schema versioning so you can track changes over time. And use contract testing between pipeline stages or between producers and consumers to ensure changes don't break things unexpectedly. Catch problems before they hit production and cause a debugging fire drill.
That makes a lot of sense. Proactive versus reactive.
And related to all this debugging pain, there are the debugging and development challenges themselves, like the inability to easily local debug some cloud-based ETL jobs like AWS Glue.
Right, you have to deploy it to the cloud just to test a small change.
Often, yeah. Which means constant deployments, waiting for logs, huge friction. And the error messages you get back are often poor or generic, lacking the detail you need. Version control, too, is sometimes manual and cumbersome and error-prone.
Sounds painful. Workarounds.
People develop workarounds like using Dockerized local Spark environments to mimic the cloud, writing custom error handling within scripts to capture more details, manually integrating pipeline code with Git for versioning, but these are workarounds, adding their own cognitive load.
So it seems like across all these challenges, observability into pipelines is the key, right?
Absolutely. Being able to easily see what's happening, spotting deviations in data types, data drifts, performance drops, before they cause major downstream problems. You can't fix what you can't see, and the mental effort of trying to piece together the picture from scattered, inadequate information is immense.
Which brings us back to the human element.
It really does, because while the technology for data pipelines is incredibly advanced, state-of-the-art even, it's the human experience as the basis for decision-making that truly leads to wisdom.
Wisdom, not just knowledge.
Right. Our sources mention a company, Integra, that emphasizes having the largest team of Level 3 data analysts. Why? Because their insight and experience are essential. They can make sense of complex data, spot those subtle drifts an automated system might miss, and provide real-world solutions that go beyond just algorithms. It's about leveraging that human wisdom to reduce the overall cognitive load of ensuring data quality and pipeline reliability.
That's a great point. Using human expertise strategically. Okay, this leads us perfectly into something really cutting edge. A potential solution for managing this immense cognitive load in large-scale data operations. We're talking closed-loop feedback control systems for data pipelines.
Yeah, this is really interesting stuff. The fundamental problem for data platform teams today, as our sources put it, is they're often managing hundreds, if not thousands, of production jobs.
Mind-boggling scale.
Totally. And they're often handcuffed by manual tuning, lost knowledge from engineers who built legacy code and left, and just the sheer volume of changes happening all the time. As one source said, change is scary for production jobs because breaking something often means a high-stress, high-cognitive load incident for the team.
Okay, so what's the new approach?
The big idea is a paradigm shift, moving from open-loop systems where jobs just run, maybe monitored but not self-adjusting, to closed-loop systems, systems that automatically adjust and optimize themselves based on feedback.
Closed loop, like a thermostat. Senses the temperature, adjusts the heating.
Exactly like a thermostat. That's a perfect analogy. So imagine a magical update config block, which in reality is a sophisticated mathematical model or maybe a machine learning algorithm.
Okay.
It takes output statistics from a pipeline run, things like how much it cost, how long it took, and it automatically adjusts the configurations for the next run. Maybe it changes the cluster size or memory allocation.
Tuning itself.
Precisely. This process iteratively drives the pipeline towards whatever business goal you've set. Maybe you want lower costs. Maybe you need to hit a specific service level agreement, SLA, for runtime. And it does this without humans in the loop for the tuning part.
Wow. So you just set the goal.
Yeah, the powers, you can set any kind of goal that's measurable: runtime, resource utilization, even energy efficiency, fault tolerance, scalability, latency, whatever matters. The system then essentially auto-heals jobs.
Auto.
Yeah, it constantly adapts to changing conditions, like growing data volumes or changes in the code, to keep performance aligned with your target, like staying below a target SLA.
Mm.
It takes a huge amount of manual tuning effort and cognitive load off the engineers.
I can see how that would free people up.
Absolutely. The sources argue this approach will dramatically help free up data platform and engineering teams to focus on actually building new pipelines and features, rather than being constantly bogged down in troubleshooting, manual optimization, and just grappling with the cognitive load of keeping complex legacy systems running smoothly.
That's the real promise, isn't it? Automating the cognitive load management itself, at least for the operational tuning.
Exactly. It's a powerful concept for managing complexity at scale.
So let's try and wrap this up. What does this all mean for us, really? From understanding those basic limits of our working memory way back with Miller,
hmm
to designing clearer, more understandable code, avoiding those cognitive traps, all the way to building these robust, even self-optimizing data pipelines. It seems this concept of cognitive load is just profoundly impactful everywhere.
It really is. Here's that old saying, right? Knowledge is knowing that a tomato is a fruit. Wisdom is not putting it in a fruit salad.
Ha! I like that.
Our deep dive today, I think, has shown that just having high-resolution data, just knowing all the facts, the knowledge isn't enough.
Right.
It's the human experience, the collective wisdom, and the deliberate design choices we make to proactively manage cognitive load. That's what leads to real wisdom and real-world impact. It's about designing for the human brain, acknowledging its limits, not just designing for the machine.
The simpler you make something, fundamentally, the more people will be able to learn it, understand it, build upon it.
Yeah.
And that applies whether you're a student trying to grasp a new complex concept, a programmer trying to craft elegant, maintainable solutions, or a data engineer building the information backbone of an entire enterprise.
It's universal.
It really seems to be about creating systems, processes, even learning experiences that truly respect our limited mental bandwidth. Cut out the noise, focus the effort.
Well said. And maybe a final thought for you, the listener, to mull over.
Okay.
If even our most complex technological systems, like these data pipelines, can become auto-healing, constantly adjusting themselves to maintain optimal performance and reduce operational burden,
Right, that closed loop idea.
what if we applied that same closed-loop feedback mindset more intentionally to our own learning and work habits?
Mm.
What if we consciously and constantly adjusted our environment, our approach, how we consume information, specifically to reduce unnecessary mental burden, to really free up our working memory for that crucial germane load, for deep understanding, for creativity?
Applying auto-healing to ourselves.
What kind of explosive growth, what kind of potential could you unlock if you systematically lowered your own cognitive load?